So the next speaker is a geophysicist, John Michael Kendall. Who is John? Okay, John. And John is at the Department of Earth and Science at the University of Oxford. So welcome, John.
Thank you. It's a real pleasure to be here. This introductory slide is a picture I took last winter when it was much colder at Lake Louise. I'm at the University of Oxford, and following on from a couple of the previous talks, there's a large initiatives in Oxford looking at how we're going to achieve net zero. And one of them that I'm involved with is called the Oxford Net Zero Program, which really describes how we're going to reach it from a regulatory policy through to science questions. The Zero Institute looks at zero carbon energy systems, but there's a nascent institute that we're just forming, which really is, at the heart of it, is how are we going to actually sustainably resource the transition to net zero. And really, at the heart of this is the use of geofluids and what we do with them and what we can get from them. It requires really a cross-disciplinary approach, so ethics, economics, engineering, through to science questions. This, as a motivation, this infographic from McKinsey really describes the challenge. Across the horizontal axis are different technologies that will be needed to achieve net zero. And along the vertical axis are the critical materials that are required. So in all of them, the top line is steel. We need tons of steel. The second line is copper, and most of these new resources require tons of copper. We need more copper in the next 30 years than human beings have consumed in their entire existence. But then as you get towards the right, the wind, solar, electric vehicles, there's a real pantheon of metals and elements that are needed in quite large quantities. We've already heard from Daniel about lithium, which is needed in electric vehicles, but there's rare earths like neodymium needed in wind and electric vehicles. And there's a real challenge in that there's an unprecedented demand for natural resources that are going to be required to achieve net zero by 2050. And so what I'm going to talk about today is a slightly unconventional place to go for metals, and that's an active volcano. And the blueprint for this work is a paper that was published by a colleague of mine, Professor John Blundy, who's a Royal Society research professor at Oxford. And working with co-workers, they basically described the economic potential of metalliferous subvolcanic brines. And I'll talk a bit more about how we explore for these. So central to the production, the making of a volcano is the concept of the Earth as the ultimate recycler. New plates are formed, where plates collide, plates go deep into the Earth, and as they descend, they take material from the surface down. It warms, it rises, the rock becomes molten, and that molten rock brings with it fluids that are very rich in critical metals, rare earth elements, that sort of thing. And through subsequent eruptions, you build a volcano over time. And what mining companies do when they look for ores is they go to places where there was a volcano millions of years ago, and they mine it looking for the ore that's left behind. And so here's a good example. This is one of the largest copper mines in the world, Cerro Colorado in Chile. And it's one of really a handful of copper mines that produce most of the world's copper. These, like I said, this is mining what was it's an extinct volcano. You're digging out a large amount of rock, pulverizing it with a very energy-intensive process to get back to the copper or the other minerals that you might be interested in. Finding these mines is really difficult. It's a real challenge and almost literally a needle in a haystack. Instead, we can actually go to the volcano before it becomes extinct. So this is a picture of Mount Etna in Italy, and it's degassing all the time. And the plot on the left shows all the different elements and metals that are emitted in the gas that's coming out of that volcano. The vertical axis is kilograms per day. So just going back to copper, copper is the red dot second from the right. This volcano emits 10,000 kilograms of copper every day in its gases. And there's a diverse portfolio of other metals also. And what's more interesting is that that's just the tip of the iceberg. There's much more stored in the deep brines, in the condensed fluids in these volcanoes. And there's over 2,000 degassing volcanoes in the world. So it's much easier to find a volcano than it is to find a copper mine. And the question is, can this be resourced in an economic way? Just to give you an idea where we're targeting in this work, this is sort of looking inside a volcano. B and C on the top are the more conventional hydrothermal systems that we get geothermal energy from. You get temperatures up to about 300 degrees. You can have gases or not. At the bottom in E, the orange lens is the hot magma body that's basically the thing that's heating the whole system. And then the sweet spot in the middle, A, is where we're looking at brines, as Daniel described, very salty fluids that are in a supercritical state. And if they have chlorine in the brines are a real carrier for metals. They latch on to metals and other valuable minerals. And it's finding this is the challenge, is what we're interested in. And this goes back to the Blundy et al. Paper, and the diagram on the right illustrates the effect of temperature on these brines. So the horizontal axis is temperature, and the vertical axis, it's a logarithmic axis, and it's copper. And it basically, each line is different salinities, but in all cases, as you go to hotter and hotter temperatures, the brines hold more and more copper. And really, by the time you get up to 510 degrees, you have many orders of magnitude more copper in the brine than you do when you're at a much cooler 300 degrees temperature. So all this sounds really good, seems straightforward, but obviously there's going to be some challenges. The most obvious one is drilling into an active volcano is perhaps not the most obvious thing to do. But there is precedent, and this is an example from Kokonda, Japan, a geothermal field where a company drilled into 89,000-year-old granite. They got down to a depth of almost 4 kilometers in 1995. They encountered temperatures of 500 degrees, and they recovered brines that were literally laden with, the scaling in the pipes was a big issue because there's just so much metals in it. And they were primarily interested in this because these deeper supercritical hypersaline brines produce much more energy. And there's new advancements in drilling technology that are making drilling like this a lot easier, for example, plasma drilling. So I think drilling is a surmountable engineering issue. The whole process, as any process in resource extraction, takes energy. So there's a fine black line that goes down into what's labeled as the conventional reservoir fluid here. We can get the heat conventionally from a geothermal system, and we can use that heat to power the extraction of the brines from the deeper supercritical fluids. And then the extraction, we can just pull the fluids up and then process it on the surface, or we can be more clever in ways actually that Daniel described, where we can introduce reactants. So you can put in a scavenger that preferentially scavenges for copper, and then you bring that fluid back out and process. And then the final thing is we have to find these things, and that's what I do. I'm a geophysicist, and we have to look for these hypersaline brines in the volcanic systems. We have a lot of experience looking at volcanoes. This is a volcano that recently erupted in Eritrea, and this is all the seismicity that was detected using machine learning methods and published last year. So we're good at imaging inside of them. We can use seismology. We could use active seismology like the oil and gas industry does very effectively in finding oil and gas. Same techniques can be used to find brines in these volcanic systems. What I work on more are using passive methods, using the seismicity that's in the volcano. We can use magnetotelluric or electrical methods because the brines are so saline, they're much more conductive than the surrounding rock. So we can use that to delineate these reservoirs. And the brines are generally less dense, and so we can also use gravity methods to survey. And by using multiple methods, we can reduce some of the non-uniqueness in exploration. So here's an example from a volcano that we studied in Ethiopia called Aluto. And what I'm showing here is the contrast between two types of seismic waves, which are very indicative of fluids. So the red in the middle towards the bottom is indicative of areas where we have partially molten rock. The blue at the top is areas where we have gas-filled hydrothermal systems. And the blue in the middle is a prospective hypersaline supercritical brine. Here's an image from Kokonda again in Japan using magnetotelluric imaging. You can see the borehole going down on the left, down to 500 degrees. The orange colors are where the material is really conductive. There's a clay cap at the top. Where it's bluer, it's where it's less conductive. And you can see that even though they got a lot of brines out, they probably missed the main reservoir of these hypersaline brines. So to conclude, I think there's some big challenges ahead to achieve net zero by 2050, and I think exciting the earth sciences are going to play a central role in delivering many of the solutions. And really, a lot of what I talked about today is resources from geofluids. I think working with industry is going to be crucial. We have an oil and gas industry and a mining industry that have worked with the subsurface for nearly a century. But we can't forget that there's still a really acute need to reduce, reuse, and better recycle the metals and the materials we already have. But hopefully I've convinced you that there's some potential in mining these hypersaline brines beneath volcanoes, because they're a really rich source of critical metals and other minerals. We can reduce the cost of geothermal energy by co-extracting metals with the geothermal energy. And volcanoes are abundant, and this addresses something I didn't have time to get into, is the geopolitical issues faced with natural resources. Having single country dependencies is not good. Even the UK has volcanoes. We have volcanoes in territorial waters. Canada has volcanoes. And then a final note, I would say, and a really important consideration is in our quest to achieve net zero, this is not done at deleterious consequences for other parts of the world. So we have to think about how we do this responsibly as a globe. So I'll stop there. Thank you.
Very nice. Thank you very much.